So in this session, I'll talk about continuous fuzz testing in Go. So before we start, how many of you wrote fuzz tests before? Okay, some people. How many of you integrated them into your CI/CD? Okay, nice. Okay, it's quite a lot actually than the usual. So hopefully this session will help you write a better fuzz test and help you understand what are the best practices to integrate them into your CI/CD. So before we start, a little bit about me. I'm the founder of Fuzzit. Before Fuzzit, I did a lot of consulting with focus on security, penetration testing, mobile, web. And before that, I did a couple of ventures, some VC funded, some not. And before that, I served at the cybersecurity part at IDF. So today we'll talk about what is fuzzing, what we should fuzz, what types of fuzzers exist, and then we'll discuss GoFuzz, which is essentially the current de facto standard fuzzer for Go, and then we'll deep dive into how to integrate it into your CI/CD, what is continuous fuzzing, some case studies, and then we'll also discuss a little bit what fuzzing is not, what it does not replace, the future of fuzzing, and we'll do short Q&A. So, what is fuzzing? Essentially, fuzzing is a way of providing semi-random input in an automated way to a program in order to uncover bugs and crashes. So the second question that I got asked a lot isn't fuzzing is only for like security and memory corruption vulnerabilities, because obviously Go is a safe language, so we don't usually have this kind of problems. So the answer is that yes, you probably won't find any memory corruption bugs in Go unless there is some bug in the Go interpreter, which is unlikely. But you will uncover a lot of bugs and improve stability and code coverage. You might find logic bugs. You might find crashes, which essentially can bring you to like denial of service of your service, and you can also look at this as a security bug, and we'll discuss this. And the other cool thing is that you will just run millions of unit tests without writing them, which is nice, because nobody really wants to write unit tests. So what to fuzz? So fuzzing doesn't work for like every software or every component, and usually there are some classic examples of software that is easily fuzzable, and it's also important to fuzz those components. So the classic examples are compressions, network parsers, crypto libraries, media formats. So those are usually also very vulnerable to some kind of like parsing bugs, and like crypto libraries. If you have a logic bug there, it might also bring to serious security issue. Network parser, like classic example is, for example, your DNS provider like Cloudflare or other DNS provider, and you have a bug, just a crash, not a security, but just a crash in your DNS parser. This will bring your whole service down very easily. So essentially, it's a must-have for anything that consumes and parses input from the outside world. Okay, untrusted input from an external user. So there are a lot of types of fuzzers. I'll discuss mainly two types of fuzzers, which is the traditional, just random fuzzer, which generates completely random input, and the coverage guided one, which uses coverage guided feedback to generate the input and proved to be very successful. Like the first fuzzers that got a lot of traction were mainly in C++, like AFL and libfuzzer, and because they were so successful in finding a lot of bugs, they were ported to different languages, also to GoFuzz. It was developed by Dmitry Vyukov. And then I ported also some of the fuzzers to Python, JavaScript, and Java. Okay, so let's look at an example. So we have a function here called parse complex. It's not really complex, just for the sake of the example. So anyone can spot the bug here? Yeah. So I heard it from the crowd. Yeah. So we have a classic off by 1 here. So what the function wanted to do is just to check if it got fuzz it, the byte array fuzz it, and return true. And if it got anything else, it will return false. But we have a classic off by 1, and if we pass it fuzz it, it will crash because it accesses the 6th element, but the array can be 5 lengths of 5, so it will access out of bound and the program will crash. It won't be like a memory corruption vulnerability because the Go runtime will catch it, but still it will crash your program. So before I show you how to run GoFuzz, I want to show you how coverage guided algorithm works, and GoFuzz works the same way. So on the left, the classic random fuzzer just generates completely random input each iteration and then execute this input. The coverage guided one have one preliminary step. It instruments the program for coverage. So after each iteration, it will be able to get what coverage did my test case hit, and then it executes in a loop, choosing a input from something we call a corpus. Corpus is just a directory with test cases. So if the directory is empty, it just generates one random input. If it's not empty, it chooses a random test case from this directory. Then we mutate the input, and I'll talk about what mutations usually those fuzzers have. It executes, and it collects coverage. If the new test case that the fuzzer generated hit new coverage, hit new path, then we add it back to the corpus. We add it back. So this is essentially a very simple generational algorithm. So the fuzzer doesn't get stuck. It always advances and try to find new coverage, hit new test cases. And this is why it was also very successful in finding a lot of bugs. So now, how GoFuzz?
So in that step, do you know what the expected output is, or you don't care?
So I'll get it. Yeah. So here we have an example of GoFuzz. So for some confusing reason, GoFuzz without a dash is the random fuzzer, which is not very good, and GoFuzz with a dash is the coverage guided one, which you want to use. So on the left side, just like I said, it generates one input string every iteration, completely random input, and then it calls our parse complex. Here you need to go get GoFuzz and GoFuzz build. You call GoFuzz build. I'll show you a demo in a second, and then you call GoFuzz, which runs the fuzzer. So the GoFuzz, the coverage guided one, will find the bug in a few seconds, and the random one won't find the bug because the probability of finding one string out of all the possible strings in the world is essentially 0, so it won't work. So show you short demo. So I have the example. That I showed you. Same example, parse complex, and I have also the fuzz test. So you have to, for the fuzz test to work, you have to implement a function called fuzz, and it gets the byte array, which is generated by the algorithm that I showed you before, and then it calls this fuzz function in a loop until essentially it finds a crash, and it outputs the input that crashed this program. So there are a few options of GoFuzz. There is like native. GoFuzz can use a native engine which implemented in Go, and also it can use libfuzzer engine. It's more of the same. I'll use a libfuzzer engine here. So GoFuzz builds. It's doing the preliminary step that I showed you. It instruments the program, and now we can. 1 second. Okay, we need to link this program to the libfuzzer. Now we can run the fuzzer. You can see ft is the number of features, the number of mini code blocks that it discovered, and you can see that it prints new feature every time it got to a new code block. So probably it discovered another byte. I'll show you the data generation in the next slide. But it found, in a few seconds, it found the string, the fuzzy string, which get the program to crash. I didn't provide any seed input, so it started from 0 and just discovered the string that will crash the program. It didn't analyze the program. It just used the algorithm that I showed you and found the string pretty quickly. Let's go back to the slides and the data generation of the random fuzzer. So it just generates completely random inputs. Of course, it won't find the fuzzy string never. If it will, you probably have to go and fill in a lottery ticket. It is your lucky day. And the data generation of the coverage guided fuzzer is as follows, but it's not all the test cases that were generated. This is the test cases that were saved to the corpus, to the test directory. So you can see that we started with an empty string, and then every time then it discovered every time it essentially uncovers new character. So it gets to the new code block if the string is of length 5, and then every time it uncovers another character, which helps the program, the coverage guided fuzzer, to get to a new mini code block. So if we go back to our example, mini code block is like if the next character is U, we uncover another mini code block, and our coverage with new coverage. So this way, every time our fuzzer uncovers the next character until we hit our bug. So it's not only a good way to uncover crashes, it's also possible to do some more interesting stuff. For example, find logic bugs. Also a classic example is if we have some kind of parser, decode and code. So we can decode, we can encode the data, then decode and assert on that if we get different results. So that way we found a bug in our, like a logic bug in our parser, which also might be a security issue if we have like crypto library, or even just encode decode also might lead to logic bugs, which essentially might lead to security issues down the way. I think this is the trophies. So GopherCon is open source. It's located under GitHub dev go-fuzz. And this is just, I think, 1/10 of the bugs that were found and are documented. A lot of them also in the core like Go libraries, which are tested quite heavily, but still a lot of bugs were uncovered with this tool. So it works. Okay, mutations. So the mutations are pretty simple, and you can also like deep dive into the source code. There are mutations like bit flipping, byte flipping, incrementing some bytes, adding more bytes, switching bytes. It's a little bit of voodoo, but they works. They are ported from AFL originally. So the same Go that you will see in GoFuzz, it's pretty much the mutations that you will see in AFL source code as well. And libfuzzer. Libfuzzer is part of the Clang compiler. So the second thing also that GoFuzz introduced, which is quite cool, called the sonar. If we have, for example, some parser that have a checksum check, even for coverage guided fuzzer, it will be almost impossible to get through this checksum check in the code and get to new coverage. So what sonar is doing when it understands that it kind of hit a wall or every like 1,000 iterations, it tries to execute the code itself to generate the interesting bytes. So this way, it is able to bypass even some basic checksum checks. So this was the understanding, and then sonar was added to GoFuzz. Okay, so solutions and what fuzzing is not. So it does not replace unit tests. You still have to write unit tests and integration tests. But maybe if your unit test looks like copy paste of different strings that you try and like thousands of copy paste, maybe you want to use a fuzz test that will cover this automatically. It doesn't replace security design, threat modeling, attack surface reduction. Like if you run a fuzz test, it doesn't say that you don't have bugs anymore. You still have bugs, but it will help you just eliminate some of those. So who is writing the fuzz tests? So as a developer, you're responsible for writing the fuzz tests because just like you write unit tests, and you are the best person to understand what components of your program are fuzzable, okay, and what components make sense to fuzz. Some challenges. Coverage. So coverage guided fuzzing works best with standalone libraries. So if you have a function, essentially, or a library that you can call, which does not doing like any, that doesn't go with like HTTP request somewhere and gets input from like a microservice, but standalone library that you can call fast. This will be very easy to write fuzz tests for this scenario, because for fuzzing also to be efficient, it has to be fast. So if you have standalone libraries, it will be very easy. Some application, even if they make sense, fuzzing, because like they are security critical, they are hard to fuzz test, and there is no like out of the box solution, and you have to do a lot of work to write fuzz tests for them. Like for example, like SSH, how to fuzz like the whole handshake. Maybe you need to disable the handshake and fuzz things after the handshake. It's not trivial. It's not a standalone library. So you'll have to do like a lot of work to make it happen. But still, it's possible. But it just will be a project. Okay, so continuous fuzzing. So running a fuzzer once is nice, and it will probably find bugs. But just like unit tests, you want to run them every time you push new code. So, but unlike unit tests, which are quick, hopefully, fuzzing can run indefinitely, and there are new questions that we need to ask. How long should we fuzz? What versions should we fuzz? And this is what I'm going to talk about. And before I deep dive into the continuous fuzzing workflow that from my experience and from our experience works well, there are a few possible options that I want to mention for if you want to build like a continuous fuzzing infrastructure for your code. So you can build it yourself. I think it will be pretty hard because there are a lot of nuances that I'll talk in a second. Like the self-hosted solution currently that I think is available is called Cluster Fuzz. It's open source. It's open source by Google. The limitations are that it requires GCP account, so you'll still be bound to use GCP, at least for now. There are, I think, some issues open in Cluster Fuzz that requested to make it like a standalone, but it's not implemented, at least not yet. The baseline cost will be about $600 per month of GCP credits, even without running a single fuzz test. This is just how Cluster Fuzz works. It started from Cluster Fuzz started from the Chromium team, as they built it to fuzz their essentially Chromium engine, which had tens of thousands of bugs, and because it's like security critical and it's written in C++ and it's JavaScript parser, so it's a classic example of a lot of bugs. The other thing is like vendor managed. So we also essentially a continuous fuzzing vendor, and we have also a free tier for OSS. So if you have OSS repository, feel free to ping me. Okay, so the workflows. There are two workflows that we found successful, integrating more than 30 open source projects, like CoreDNS, systemd, a lot of CNCF projects. The first workflow is the fuzzing workflow, where essentially we find bugs. So every time we push new code to the master or to the development branch, you build the fuzzers in the CI. So we have integration with any CI. Those workflows work for Cluster Fuzz or for any continuous fuzzing that you can build. They're essentially the same, but I'll talk about how we integrated it. So you build the fuzzers in the CI, and you upload them to a server where you need to run those fuzzers. You run them until you find a crash, and then you have to catch the crash and report it. Or until a new version of the fuzzer is uploaded. The important thing is to save the corpus between runs. So every time, for example, you push the code once a day, once an hour, every time you build a new fuzzer, a new version of the fuzzer, you don't want the fuzzer to start from the beginning. You want essentially the fuzzer to start from the same place where the old fuzzer stopped. So you have to save the corpus, the directory with the test cases. Because you want essentially the fuzzer to fuzz only the new code that was added in that version. So this is the workflow to find new bugs. Another workflow that helped a lot of our open source projects is a regression workflow. So every time you open a pull request, or someone opens a pull request with a contribution, so this workflow you can run inline in the CI, because this workflow is fast. You download the corpus, you download all the test cases that you fixed, and then you run the fuzzers through all the files available in the corpus. So this is something quick because you're not really fuzzing, you're just running those fuzzers through the test cases and the crashes that you already fixed, and then you can find either new bugs or bugs that you already fixed but someone introduced them again. And this is very helpful, not only for open source, but for example, for open source projects that have contributions from people that are doing, for example, one contribution. They're doing the contribution, someone is reviewing, merging the pull request, and then after the merge, they find out that they crash one of their fuzzers. So this way, and then the person disappears, and you have to fix it. So this way, you can find those bugs before in the review process. So continuous trophies, just an example of good examples of two bugs that we found. So one bug actually one repository had already fuzz tests, but it just the repo didn't have like the fuzz test running every time it pushed new code. So we just integrated the continuous fuzzing, and we found essentially new bugs with the same fuzz tests. So it's important to have your fuzz tests essentially running every time you push new code, because why not? It's automated, and you already wrote the fuzzers. That's the hard work usually. And the second thing is that we found some bugs in compression libraries after running them for 10 hours. So you don't usually run the CI for 10 hours, but this is something that is easily done in CI that is built specifically for fuzzing, because we know that fuzz test runs for a long time. Okay, so future of fuzzing. So as you probably saw, like the fuzz function that you need to implement in Go gets just a byte array, and if you have something that gets more complicated input, then you have to do the transformation yourself. Like you have to transform the byte array to your struct. So there is a lot of work around that people are doing of providing this out of the box for GoFuzz or for other fuzzers that will give you the ability to introduce more complex input to your program and without writing the transformation yourself. And there is also work, this is related to Go, to turn fuzzing to be part of the Go standard library. Thank you.